Hello, in today's class we are going to look at the reciprocal space and how it relates to the real space. So far we have looked at reciprocal space as an independent entity, or at least that is how we have focused on it. We have had a definition for what is reciprocal space, how it relates to some quantities in real space, and on that basis of that relationship we derived a lot of properties for reciprocal space. But in general we looked at that relationship, that first set of equations we wrote saying if you have a1, a2 and a3 as the real lattice vectors, then the relationship between b1, b2 and b3, the reciprocal lattice vectors corresponding to those real lattice vectors, we wrote a relationship. That relationship between a and b was arbitrary, and I did tell you that we can select some relationship and then you will see some properties, but we chose to a particular relationship. So we said b1 is a2 cross a3 by the volume of the unit cell, etc. So we wrote up some relationship. It was at that point an arbitrary relationship, and then we proceeded with it. We got a lot of useful properties for the reciprocal lattice, corresponding reciprocal lattice. What I am going to show you today is that that relationship is not really all that arbitrary, it has some significance. The significance is that the real space and the reciprocal space are related as Fourier transforms of each other. The reciprocal space is the Fourier transform of the real space and vice versa. So we are sort of going to look through some mathematical derivation process that we will go through, which will show you that the reciprocal space that we generate, the definition that we give for the reciprocal space that we are typically using for the reciprocal space it comes about naturally if you treat it as a Fourier transform of the real space. So this is what we are going to do. Okay. So to do this we are going to take a 4-step process, and so I am going to put down those 4 steps. We are mathematically going to do a bunch of activities related to each of those 4 steps. When we finish the 4th step, you will have this final relationship that the reciprocal space is a Fourier transform of the real space. So this is what we are going to do. So we are going to start by, first of all, we are going to write an expression, write a mathematical expression for a 1D real lattice. So we do need a mathematical expression for a 1D real lattice, because it is using that mathematical expression only we are going to do further analysis and then arrive at a mathematical expression for the corresponding reciprocal lattice, and then or at least we are going to do something and we are going to arrive at an expression, and then we are going to see that whatever is the reciprocal lattice that comes is a Fourier transform of this lattice that we have started out with. Okay, so we need to write a mathematical expression for the 1D real lattice. Then we need to determine the Fourier coefficients corresponding to the Fourier series of this 1D lattice, of the 1D real lattice. Okay. So we write a mathematical expression for a 1D real lattice, then we will determine the Fourier coefficients corresponding to the Fourier series of this 1D lattice. Then we will look at a derivation for something that is referred to as the Poisson's summation formula. So we will look at a derivation for something called the Poisson's summation formula, which relates the Fourier coefficients of a periodic function to its Fourier transform. Okay. So, we are going to look at a derivation of the Poisson summation formula which relates the Fourier coefficients of a periodic function to its Fourier transform, and using all of these, using the Fourier coefficients of the 1D real lattice using the Fourier coefficients of the 1D real lattice and the Poisson summation formula. We are going to show that the reciprocal lattice is the Fourier transform of the real lattice. Okay. So, these are the 4 steps that we are going to do. Of course, I am doing this in a 1D example is what I am going to do. In principle, similar analysis can be done for 2D and 3D. We will stick to 1D, it is a simpler analysis and it conveys the idea which is all we are interested in. So, at the end of it, so we are going to write a mathematical expression for a 1D real lattice. We are going to determine its the Fourier coefficients corresponding to the Fourier series of this 1D real lattice. Independent of this, we are going to look at a Poisson summation formula which will relate the Fourier coefficients of a periodic function to its Fourier transform. So, now we have 2 pieces of information. We have the Fourier coefficients for a 1D real lattice and we know a way of relating those Fourier coefficients to the Fourier transform of that 1D lattice. So, if we do those 2 things using the Fourier coefficients of the 1D real lattice and the Poisson summation formula which will relate this Fourier coefficients to the Fourier transform of that 1D lattice, we will find that the Fourier transform of the 1D real lattice is the same thing that we would normally use as the definition of that reciprocal lattice. Okay. So, therefore, we will when we finish this, we will appreciate the fact that the reciprocal lattice is not some totally arbitrary definition, but is actually related to the real lattice through a Fourier transform. Okay. And recognizing this actually opens up the doors in a big way, because mathematically there are various properties that Fourier transforms have and so on, and this kind of a relationship, knowing that it is these 2 are related as a Fourier transform enables you to use all those properties for the real space and the reciprocal space. Okay. So, this is what we would do. So, let us start with the first step, which is writing a mathematical expression for a 1D real lattice. So, what is a 1D real lattice? We have a lattice point, then we have nothing for some distance, we have another lattice point, nothing in the middle, yet another lattice point, and so on. So, we have lattice point, nothing in the middle, lattice point, nothing in the middle, lattice point, nothing in the middle, and so on. So, we need a mathematical expression which will simulate this, which basically will represent this. So, you will need something that has a value only at a specific location. You need a function that has a value only at a specific location, does not have a value anywhere else, and then that kind of a function we are going to put up periodically. So, those are 2 things that we are going to do. So, a function which enables you to do this is referred to as a delta function. Delta function is a function which is defined such that it has a value only at one location, it does not have a value anywhere else, and so we are going to put up a series of delta functions at various points. So, that is what we are going to do. The way it is defined is it has a few aspects to its definition. The one that immediately is relevant to us is that the function delta of x is equal to 0 for all x not equal to 0. So, as long as this argument x is not equal to 0, this function will evaluate to 0. It will evaluate to a value only when this x is equal to 0. only at that value of x is 0. So in other words, it is defined only at x is equal to 0, it is not defined anywhere else, okay. And also in terms of its value, it will work out to, it is defined again like this, the integral minus a to say plus b such that it goes through the origin of delta of x dx is equal to 1, as long as region of integration includes the origin. So, the way I have written it, going from some minus quantity to a plus quantity, it goes through the origin, therefore, this integral integrates to 1, evaluates to 1. Okay. So, this is another property of this delta function, and now the way I have, so this is going to evaluate to 0 at all other values except at the origin, at all other values of x. So, at all other locations it is going to evaluate to 0. So, it uniquely puts up a value only at one point, that is the point of this function, and if you do an integration of this function over this region, it will evaluate to 1 around this point. Now, this is a function that is now, the way I have written it, it has a value only at the origin, which is x is equal to 0. Supposing you want to put this function at some other location, at say x is equal to a. So, the way you would rewrite this function is simply define it as delta of x minus a. Okay. So, now this puts the delta function at a location a, because this argument evaluates to 0 only when x is equal to a, right. So, so this is so similar to this point that we have written here, we can say that delta of x minus a is equal to 0 for all x not equal to a. Basically it is defined at 0. So, instead of setting x to be equal to 0, we are setting x minus a to be equal to 0. So, x minus a will be 0 whenever x is equal to a. So, this forces this delta function, instead of, if this were the origin, you can now, by using this kind of definition, you can force this delta function to show up here, and if this spacing was a. Similarly, if you want to put it at 2a, you will have to put x minus 2a and so on. So, you can have a series of such points, right. So, this is one aspect of the delta function, and incidentally one of the features, because of the way it is defined, because it shows up as being 0 at all other locations and has a unique value, when you integrate it, it integrates to 1 as long as you go through the origin. One of the interesting features that this function provides you is that if you multiply this with any other function, okay, so that function will also, that product will now evaluate to 0 at all values other than the origin, right, because at all other values of x, if you multiply, so if you write f of x you create a situation that this is going to evaluate to 0 at all values of x not equal to 0, because this function is equal to 0 at all values of x not equal to 0. So, it will only have a value at x equal to 0. So, this will if you do this integration, you will if that region of integration includes the origin, then this evaluates to 1 around the origin. So, this will basically evaluate to 0, f of 0. This is so the integral of this f of x times delta of x dx will evaluate to f of 0. So, similarly, if you put in the same function at some other location, when if you create your delta function like this, such that it is now positioned at a location x is equal to a, then you can write f of x delta of x minus a dx. If you integrate this, say minus infinity to plus infinity, whatever you integrate it such that it includes the region x is equal to a. Primarily it has to include the region x is equal to a, include the location x is equal to a. This will evaluate to f of a, that is all it will evaluate to. So, region of integration should include a. So, region of integration should include x is equal to a. If you include x is equal to a, this will evaluate to f of a. Okay. So, this is the function. So, now we have some properties for this delta function. We understand that by putting this delta function, not all of them are immediately necessary for defining the I just wanted to put it down so that you know what are the properties of the delta function, because we are going to use some of these properties. But we are right now at this stage, we are simply looking at a function to represent the 1D lattice, and we find that the delta function provides you with some of the important features that are necessary for it. So, what we need really is a delta function that is available at each of these locations. So, what we are simply going to do is we are going to take a series of delta functions and put a sum, so that you get now a sequence of delta functions, and each term will now create a delta function at each of these points. So, that is what we are going to do. So, therefore, you can write this the function f of x, which will represent this 1D lattice, is basically simply going to be a sum of say n going from minus infinity to plus infinity of delta of x minus NA. Okay. So, this function f of x, which is a sum going of n going from minus infinity to plus infinity of a delta function x minus NA, creates a situation where you have a delta function at each location, because when n is equal to 1 you have x minus a, that will create a function, if this were the origin, that will put a delta function at x is equal to a. If you have n is equal to 2, it will create a delta function that will become valid only at x is equal to 2a, because at 2a minus 2a will give you 0. So, that will create a delta function at this position 2a. Similarly, at n equal to 3 you will get a delta function here, and so on. So, this is a function that now represents your 1D lattice. Okay. So, we now have a mathematical expression for the 1D lattice, which is the, if you come back here, the first step that we said we will do is to come up with a mathematical expression for a 1D real lattice. So, we have now gotten mathematical expression for a 1D real lattice. The next step we are going to do is to determine the Fourier coefficients corresponding to the Fourier series of this 1D lattice. Okay. Right. So, if we have a function f of x, so the Fourier series corresponding to this is basically given as 1 by it is basically a sum n is equal to minus infinity to plus infinity c of n e to the power 2 pi I n x by a. So, if you take a periodic function and then you write it as a series of in the terms of a Fourier series, then this is how the Fourier series would be written as. In this class we are not really looking at the derivation of a Fourier series or of a Fourier transform. So, I am going to assume the definition of a Fourier series and a definition of a Fourier transform. So, if you are not familiar with the definition of a Fourier series or a Fourier transform, so that alone is something you will have to look up. That definition is simply I am just going to use it here. So, this is how it would be defined. You will have a function f of x, and we would write it as a it is a periodic function, and it is now written as a sum of a series of terms and basically an infinite series of terms, which will have this general format. A Fourier, this Cn is called a Fourier coefficient and of this Fourier series. So, for each term you will have for every value of n you will have a coefficient value, and corresponding to that you will have this Cn e power 2 pi I n x by a, where a is the periodicity of that function. Okay, so, this is how we would go about it, and each of the Fourier coefficients itself Cn would be defined as 1 over a integral minus a by 2 to plus a by 2 f of x e to the power minus 2 pi I n x by a, or n x over a. This is how you would write it dx. So, this is an integral. So, this is how we would write it, right. So, each of the Fourier coefficients is written like this. Now, our 1D, so this is by definition sort of definition of what a Fourier series is. So, you can look that up. Now, for us, for the 1D lattice, the f of x is basically we have written it as a sum n going from minus infinity to plus infinity of delta functions x minus n a. So, now if you look at the Fourier coefficients of this 1D lattice, that is simply going to be 1 over a integral, we can put the sum here, okay, n equals minus infinity to plus infinity, integral minus a by 2 to plus a by 2 delta of x minus n a e to the power minus 2 pi I n x by over a dx. So, this is now the Fourier coefficient. We have simply substituted the fact that our 1D lattice is represented by this function into this equation. So, that is what you have we have got here. Now, we also noted one property for the delta function, which we will come back here and see. We noted that when you have a delta function f of x times that delta function x minus a dx, if you do the integration, if you include the region, if the region of integration includes that value x is equal to a, you will it will simply evaluate to f of a, right. So, f of x will simply evaluate to f of a because of the properties of this delta function. So, the same property we are now going to utilize. So, here we have the delta function, it is not simply x of, so basically you have this delta function and you have a function f of x here. So, this if it, as long as it includes this region of x is equal to n a, you will basically you will find that this will evaluate to f of a, and correspondingly each of these terms will it will add to those terms in those respective locations. So, this is going to evaluate to f of a, and in particular in this case you are going to see 2 pi I n x by a. So, this simply become 2 pi I n 2 pi I, and e to the power I theta is simply cos theta plus I sin theta. That is how the e exponential function is. This function here is being defined by that, e power I theta is cos theta plus I sin theta. So, when you have 2 n pi as the argument there, cos 2 n pi plus I sin 2 n pi, 2 n pi I sin 2 n pi will evaluate to 0, this will evaluate to 1. So, we simply basically have 1. So, therefore, this f of a, this is basically going to be e power 2 pi minus 2 pi I n a by a is what we are going to get, and therefore, this whole integral that is here will always keep evaluating to 1. For all values of n, this whole thing will evaluate to 1 because of the property that we see for the delta function times the some other function. This happens to be the some other function that is there. So, it will only have the value of this function at the value of a, and therefore, it will evaluate to 1. Therefore, all the Fourier coefficients will now evaluate to 1 by a. So, you see here C subscript n. So, this is a Fourier coefficient. So, it could be C1, C2, C3 etc., and minus infinity to plus infinity. So, you have a lot of terms here. All the terms here will evaluate to 1 by a. So, that is the point that we need to know regardless of the value of n. So, we have now done the second step which of our derivation here. We wrote the mathematical expression for 1D real lattice. We have written the Fourier coefficients corresponding to the Fourier series of the 1D real lattice. So, now we are going to look at the third thing, which is look at a derivation of something called the Poisson summation formula, which relates the Fourier coefficients of a periodic function to its Fourier transform. Okay. So, this is what we are going to do. So, if you take a periodic a function f of x, periodic function, and you write it as a Fourier series. So, it is written as a infinite, it is a sum of infinite set of terms, all of which have a periodicity 2 pi, and so 2 m pi. So, basically you can write this as sum of n is equal to minus infinity to plus infinity g of x plus 2, so we just use m here, 2 m pi. Okay. So, basically if you have a periodicity of if you have some periodicity, then the function at the value of x will be the same as the function of the value. So, f of, if some periodicity is there, if the function at some value x will have the same value at x plus that periodicity. That is the way in which we are defining the periodicity, right. So, a function will have some value at the argument x, and then if you go increase that value to x plus the periodicity, it will come back to the same value of whatever is that value of the function. So, function keeps getting the same value at that periodicity. So, that is the idea of it, and therefore, if the periodicity is say 2 m pi in this case. So, g of x will be the same as g of x plus 2 m pi. That is why you end up saying that that is the periodicity of that function. So, that is what it is. So, you get this, so we can represent this function using a set of infinite terms which have this kind of a periodicity, and that is what your that is the general way in which you would express this as a Fourier series, right. Now, if you want to get the Fourier coefficients, corresponding to the series, then you will have C of n is basically 1 over 2 pi integral 0 to 2 pi f of x, or in this case you will have g of f of x e to the power minus 2 pi I n x dx by a dx. Okay. So, this is what your Fourier coefficients is going to look like. This f of x is this term here. So, we are just going to put that here, because 1 over 2 pi integral 0 to 2 pi and there is a sum here. So, I just put the sum here, m going from minus infinity to plus infinity of g of x plus 2 m pi e to the power minus 2 pi I n x by a dx. So, we basically get this. So, it is they are both integral, these are integral values of n. So, we can even use the same value here. So, now basically if you see here, when x is equal to 0, this is basically 2 m pi, g of 2 m pi. When x is equal to 2 pi, this is 2 pi plus 2 m pi. So, 2 m plus 1 pi is what we have, right. So, when x is equal to 0, this will be g of 2 m pi, right, and when x is equal to 2 pi, this is g of 2 pi plus 2 m pi equals g of 2 into m plus 1 pi, right. So, I can just change the limits of integration to go from 2 m pi to 2 m plus 1 pi and then just convert this to x, g of x. So, we are simply changing the limits of integration and correspondingly adjusting this function so that the process remains the same. So, instead of going from 0 to 2 pi and having this function being x plus 2 m pi, I can go from 2 m pi to 2 m plus 1 pi and have this simply as g of x. So, that is all we are going to do. So, I am just going to rewrite this with changing the limits of integration. So, this is 1 over 2 pi integral, we still have this m is equal to minus infinity to plus infinity integral 2 m pi to 2 m plus 1 pi g of x e to the power minus 2 pi I n x by a dx. So, C of n is basically this. So, C of n is this function that you see here, right. So, I have simply changed the limits of integration corresponding from 0 it has become 2 m pi, from 2 pi it has become 2 m plus 1 pi, and therefore, correspondingly this function has changed from x plus 2 m pi to simply x. So, when it is x, it is when it so you can correspondingly see, we just saw here how they are equivalent. Now, the interesting thing to note is you are now summing from minus infinity to plus infinity and you are integrating from 2 m pi to 2 m plus 1 pi. So, essentially m is changing from minus infinity to plus infinity and at the same time you are integrating from 2 m pi to 2 m plus 1 pi. It is the same as saying that you are integrating from minus infinity to plus infinity, right. You are doing two things here, you are doing a sum and an integration which are together, and in the process you are going from minus infinity to plus infinity. So, this is also effectively an integral from minus infinity to plus infinity. So, this whole thing can be combined into a single integral going from minus infinity to plus infinity. So, mathematically this can simply be written as 1 over 2 pi integral minus m going from minus infinity or minus infinity to plus infinity of g of x e to the power minus 2 pi I n x by a dx. Okay. So, what we have done is we have written a formula for the Fourier series corresponding to a function and we have recognized that it has a certain periodicity and that is why it is written in a certain way, and then we wrote the Fourier coefficients, the expression for the Fourier coefficients corresponding to a function. We have introduced that function here, and so that is the expression for the Fourier coefficients corresponding to that function. We notice that there is a sum, we then change the limits of integration because that is works out convenient for our understanding here. So, from 0 to 2 pi we change to 2 m pi to 2 m plus 1 pi, correspondingly change the function so that the form is still being maintained, and then we recognize that since we are doing with respect to m we are doing sum from minus infinity to m plus infinity and an integration from 2 m pi to 2 m plus 1 pi is the same as integrating from minus infinity to plus infinity. That is basically what it is, because at minus infinity this would be minus infinity minus 2 infinity pi and this would be plus 2 infinity plus 1 pi. So, that is why it is same as going from minus infinity to plus infinity. So, 1 over 2 pi minus infinity to plus infinity g of x e to the power 2 pi I n x a by dx, I mean n x by a n x over a by times dx. So, this is the expression. Interestingly, again I am going to use a definition which is there for Fourier transforms now. So, that definition again we are not deriving here. So, Fourier transform definition is something that you would have to look up, but this is basically the Fourier transform of your original function f of x. This expression that is written here, this integral that you have written that is written here is the expression for the Fourier transform of the function. So, this is nothing but 1 over 2 pi okay. So, this is 1 over 2 pi f tilde k. So, this is the Fourier transform of the function. Okay. So, we started with the function f of x, the Fourier transform of it is typically represented with this f with this tilde mark on top of it with a new variable k such that the k and x are conjugate variables, they relate to each other through a Fourier transform, and this is the expression you are getting. So, now this is the expression also which is the Fourier coefficient of the function. Okay. And in our case the function that we are if you take the so this is in general, right. In general you have a Fourier series, you have a function, you have it has a certain periodicity, and when you evaluate that function you look at its Fourier coefficients and what those Fourier coefficients represent, you find that for the function which if it has a certain set of Fourier coefficients, then those Fourier coefficients can be related to the Fourier transform like this. Okay. So, this C of n equals 1 by 2 pi 1 or 1 over 2 pi f tilde k. This is basically what we have done here is we have sort of looked at one derivation for the Poisson summation formula, which relates the Fourier coefficients of a periodic function to its Fourier transform. Okay. So, this is the Poisson summation formula, and please note this is C of C subscript n. So, it can take several values C1, C2, C3 etc. It can have several values. Okay. So, we have got specific things done, we have basically got a few important relationships here. We have of course first of all written the a mathematical expression for a 1D real lattice. We have arrived at the Fourier coefficients corresponding to the 1D real lattice, and we have also independently seen that the Fourier coefficients of a function can be related to the Fourier transform of the function, right. So, this is what we have got. So, we now have only the if we go back to what we started out with, if we come here we will take a look. So, we finished the step 1, we have finished step 2, we have still finished step 3. We are now going to, in the last step we are simply going to relate the parameters that we have obtained. We have the Fourier coefficients of the 1D real lattice, and we also know how in general the Fourier coefficients relate to the Fourier transform. Okay. So, using that we are going to look at how the 1D real lattice, the reciprocal, the Fourier transform of the 1D real lattice represents the reciprocal lattice. Okay. So, we see that as part of through the Poisson's summation formula that the Fourier coefficients of the periodic function have this form. C of n is given as 1 over 2 pi integral minus infinity to plus infinity g of x e to the power minus 2 pi I n x over a dx. So, this a is the periodicity of that function. So, that is how we get that a, and then n is the as an integral number, is an integer. So, now if you look at this, the term that you have here within this integral is mathematically the Fourier transform of the function g of x. So, we are not deriving the Fourier transform formula, but this is the form you will arrive at if you did a Fourier transform, and you take a function g of x and you did the Fourier transform, this is the form that you will get, and this gets represented as f tilde k. Please note, now we were working with a variable x, we have shifted to a variable k, and this f tilde k is the Fourier transform of g of x. So, these are two different variables. In a moment I will tell you something about a general relationship between them, but this is f tilde k, and so this whole thing works out to be the Fourier transform of this function g of x represented by f tilde k. Therefore, you can write now C of n is equal to 1 over 2 pi f tilde k. So, this is the Fourier coefficients of the series that corresponds to a periodic function g of x, and they are now related to the Fourier transform of that function, and that was the whole purpose of the Poisson summation formula, to relate the Fourier coefficients of a function to the Fourier transform of that function. Okay. Now, we also saw that for our periodic function, which is the lattice, a one dimensional lattice, we found that the C of n is equal to 1 of a for all values of n. So, for all values of n it would keep evaluating to 1 of a 1 over a, and therefore, if you equate these two for our linear lattice, one dimensional lattice, if you equate the result that you get through the Poisson summation formula with the actual Fourier coefficients that we are getting for the one dimensional lattice, basically this means this is 1 over 2 pi f tilde k. Therefore, you have f tilde k is equal to 2 pi over a for all values of n. So, that is the general result that we are getting. I also said that we have shifted from x being the variable, we have shifted to k being the variable, and that is typically what happens. You will have a pair of variables when you do a Fourier transform, you will go from sort of one space to another space. In general, these variables will be inversely related. So, in general, as part of the Fourier transform process, you will have k to be inversely related to the value to the variable x, and therefore, typically we will write k equals 2 pi over x, 2 pi n over x. N to pi over x is the general form of the relationship between k and x, and that is why. So, for example, if you have time as the variable, you will get frequency 2 pi over time is what you will get. If time is the variable x, then the k variable will work out to be the angular frequency 2 pi over t, and similarly if you have a wavelength as the x, you will get wave number, something like that. So, you will sort of have inverse relationship between these variables in this relationship. So, now we also see that for our linear lattice, we are not looking at all values of x, we are only looking at specifically at values of x equal to specific values of a. So, x is equal to a in steps of a is what we are looking at. So, in general k will have the form 2 pi n over a or 2 n pi over a. Okay. So, this is the typical form you will have. So, now we have two things here. We have the Fourier transform which works out to a value of 2 pi over a, and the variable itself has this general form 2 pi n over a, where a is the periodicity of that function. So, if you take these two together, we find that essentially if you look at our original one dimensional lattice, we basically said that it only has values at specific values of a. Okay, so, rest of the place it does not have a value, and so we wrote this as f of x equals sum n equals minus infinity to plus infinity a delta function x minus na. This ensured that whenever x has integral values of a, this function has a value, otherwise it is undefined, and then that is how we so this, by the way, since it ensures that there is a function only at specific locations, it has a, it is basically a spike at specific locations, it is effectively a function that sort of looks like that. And so on. So, this is it looks like a comb, so it is referred to as a Dirac comb. Is the term that is used for it. Now, we have a similar situation for f of f tilde k. We see that it has to have values of, if we come back here, we see that it has to have values of 2 pi over a, but it can have these values only at specific values. So, we are only, I mean, these are defined only, these are defined for all values of n. It is going to be 2 pi over a at all values of n, and the k itself has this this particular value. So, it is also defined only at values of a, k itself gets defined at values of a, and you have the function itself being defined as 2 pi by a at all values of n, which correspond to this expression that you have here. So, at all values of n, this variable will be this will evaluate like this, and at those values of n, this variable should always evaluate to this Fourier transform should always evaluate to 2 pi over a. So, it should be at 2 pi over a at integral values of n, with this being the variable. So, therefore, in a very similar fashion, we can write that here as 2 pi over a sum of n equals minus infinity to plus infinity delta function again. This time the variable we are looking at is k minus 2 n pi over a. Okay. So, what we see is the Fourier transform will get the value of 2 pi over a at integral values of n, and this is 2 pi over 2 n pi over a. So, this will keep evaluating to 0 at integral values of n, and then this will basically give you that delta function. So, and only under those conditions it will evaluate to 2 pi over a. So, therefore, so just the way you get this f of x as a Dirac comb, you get the Fourier transform of the function also as a Dirac comb, except that it is an inverted notation. So, you have 2 pi over a where you originally had a. So, where you had a, you now have 2 pi over a, 2 pi over a is what you are getting. So, a real lattice, real one dimensional lattice gets represented as a Dirac comb and has linear dimensions of a. It is the Fourier transform of it comes out to also to be a Dirac comb. So, that is also, it also means that it is also a spot pattern of similar to a specific set of spots that you see here, or specific locations that you see here. This will also work out to specific points. So, what is a here will now become 2 pi over a here. And so, this is the result that we are getting from the mathematical part of it, where we have just taken a function which represents the real lattice. We have found out the Fourier transform of it using the Poisson summation formula, with the help of Poisson summation formula, and then we find that the Fourier transform of it is also a set of a discrete set of points, except that the spacing between them is 2 pi over a. So, a Dirac comb of spacing a, the Fourier transform is a Dirac comb of spacing 2 pi over a, and as you can see, this form is the form that we have seen through our earlier classes as the reciprocal spacing of this spacing here. So, therefore, we see that the reciprocal spacing, so this is basically reciprocal space. So, we have seen here that we take the real space, you do the Fourier transform and you arrive at the reciprocal space. So, therefore, the real space or reciprocal space So, therefore, we are able to see that the reciprocal space is the Fourier transform of the real space. Reciprocal space is the Fourier transform of the real space. And so, this was the exercise that we wanted to do today. You can see that all the mathematics that we have done has shown us that this is the case. Previously, we had been defining this independently, and looking at properties between the real space and the reciprocal space. Now we see that mathematically we are able to go from writing down an expression for the real space, writing down the Fourier transform of it, going through the Poisson summation formula to understand the relationship between the Fourier transform and the Fourier series and the Fourier transform, and then seeing that the Fourier transform actually implies that you have arrived at the reciprocal space. So, just to sum up, we started by first writing a mathematical expression for a 1D real lattice, then we determined the Fourier coefficients corresponding to the Fourier series of this 1D real lattice. So, we had the Fourier coefficients. Independent of that, we looked at something called a Poisson's summation formula, which related Fourier coefficients of a periodic function to the Fourier transform of that function. Now, taking point 3 and point 2 together, we related the Fourier coefficients of the 1D real lattice to the Fourier transform of the 1D real lattice, and then in that process we realized that the Fourier coefficients of the 1D real lattice and the Poisson summation formula create this situation that the reciprocal lattice is essentially the Fourier transform of the real lattice, or we are able to recognize that the reciprocal lattice is the Fourier transform of the real lattice. So, this is the process that we have done, and it shows you how real lattice and reciprocal lattice are related as a mathematical entity. Okay. So, with that we will conclude this discussion, and hopefully you will find this realization of this relationship useful in many of the things that you are trying to do. Okay. So, with that we will halt. Thank you.